basically want to talk about why I think it's important for engineers or designers to learn things like machining, 3D printing, CNC, laser cutting, like basically all the manufacturing techniques that are out there. I think that if engineers can learn to do this with their own hands, they become better engineers. So I won't be talking about things like general design guidelines for DFM, that kind of stuff, or like, you know, the product lifecycle prototyping, because there are a lot of other resources in that space. I kind of wanted to give a little bit of a different flair on this type of stuff. So, who is Misty West? I'll just skip that. Like, actually, I'll talk a lot about that. So, who am I? I'm actually an electrical engineer with a biomedical specialization from UBC in Vancouver, Canada. I'm a design engineer at Misty West. Although I'm an electrical by training, I've kind of just become an electromechanical. So I do a lot of magnet, I do a lot of firmware, I do a lot of electrical as well. And I have really deep roots in prototyping and making things. So I've only been with Misty West since November of last year, but for the past 5 years before that, I worked in a genome sequencing facility, and we had our own machine shop. We did a lot of prototyping, made a lot of things for the lab. So I'm very familiar with CNC machining, manual machining, 3D printing, basically like a lot of the manufacturing techniques. I've worked in imaging, lab instrumentation, hydrogen fueling, genomics, automation, robotics, and wearables as well. So the question most people ask me when I bring this subject up is why? Like, why as an engineer do I need to know how to make things? Like, I'm a good CAD designer, why can't I just 3D print it, or I'll just outsource it, blah, blah, blah. So I will hopefully give a lot of examples and tips and tricks that I personally learned throughout my career to kind of convince you that it's worthwhile doing. So obviously 3D printing can't solve everything yet. A lot of you guys know this Gartner hype cycle. So 3D printing originally was kind of around here. Everybody thought it would change the world. Realized that actually didn't happen, hit the tropical disillusionment. It's now coming back up. I mean, you're seeing like desktop metal, you're seeing carbon 3D, you're seeing a lot of really interesting tech coming out for 3D printing. And it's enabling a lot of different things. But it's still not there yet for people like you and me. You know, metal 3D printing, carbon 3D, these guys are working with like big companies, right? They're working with Boeing, they're working with people with lots of money that they can partner with. So although the future looks very enticing, it's still not there yet for everyday engineers. So. And also, like, if you end up designing a product that goes to mass manufacturing, you're still going to end up going to injection molding. Injection molding, traditional manufacturing techniques, they're still going to be around. Molding still requires machined molds. Well, there's like caveats that, but like in general, molding still requires machined molds. So like, you still need to learn this stuff, or it can still help. Another reason why, you know, having hands-on experience making things is important because you can design better parts. So this is just a very simple example of a 3D printed FDM part. So the top left is kind of a poorer design. It's still fine, but if you know a bit more about the 3D printing process, if you've done it a lot, you kind of know, like, there are two problems with this design. One is that the bottom face that you will likely 3D print it on requires support material. And so we have a dual extrusion 3D printer at Misty West, and it has soluble support. Soluble support is kind of a pain in the ass because you either have to move it off, and it takes a long time, or you have to actually dissolve the support, which also takes a long time. So a better design is to just try to mitigate the amount of support material that you have so that you can get your part faster, you can iterate more quickly. Another thing is, if you understand a bit more about the 3D printing process, you know that for FDM at least, it prints layer by layer. So those pins that you see there for alignment of like a mating part are more likely to shear off. So knowing these kind of things can help you design a better part. So on the bottom you'll see that's a much better design because now you can print with less support, and also if you just make blind holes and put dowel pins in, your alignment features are much stronger. This is another example of FDM. I won't talk about 3D printing all the time, I promise. But again, if you understand a bit about the process and how it's made, you know that in general with plastics, you know that if you thread plastics and you're putting screws in and out, that thread's probably going to strip anyway. But for 3D printing, it's even worse, just because of the infill and because of the layer by layer process. So again, knowing that, you can make better choices, better designs. You can use something like set and series. Another example, so as I mentioned, I have a lot of background in machining. So this is often the kind of stuff that I see for people who are just starting out, or like early engineers who don't have a lot of hands-on experience, so they kind of make these mistakes. So a common feature or design that you want to impart is you want to have a pocket with a mating piece in it. Well, if your mating piece is a square, what do you do? Like, so on the top left is something that is just not manufacturable. I mean, there are ways to do it. You can use something called EDM. In general, with CNC, like you can't do that. So some tips and tricks are that for CNC, you use cylindrical endpoints, and that's how you cut away the material process. So if you try to make a square corner or a really tight corner, you end up having to use a really, really small end mill because it has to go, like the radius has to be really small so that you can get a sharp corner. But that means that if you think about how the machining process works, you're taking this tiny little end mill and you're cutting this giant pocket. So that's A, really time consuming, which translates to cost when you're designing, and also B, your tool is more likely to break. So a common like design tip or rule is to always try to maximize the radius that you have in a pocket and try to think about like, well, how is this made on a CNC machine? What is the best process of doing this? And so the bigger the end mill that you can use, the better. And then another tip is that if you do actually have to have a square part made into a pocket, you can do what we call like Mickey Mouse ears. So basically you drill a hole in each corner and then you can use a big end mill to cut everything else away. Another thing here is that for really deep pockets, again, if you have a tight corner radius and really deep pockets, you're going to end up in a lot of trouble because tools deflect, right? And again, this is a reason why learning how to do this yourself is really important, because this kind of stuff, I mean, like you can read design guidelines and like you can learn just from like anecdotally, right? This is what we should do. But if you're actually experiencing this like yourself, you realize, wow, okay, like I broken 5 end mills trying to do this, or like my tolerances are way out of whack. Why is that? So once you've gone through the process, you kind of understand where, well, my tool is deflecting, my tool is too thin, and this isn't a very manufacturable way to do it. So you learn a lot about the process from doing it. So another reason why I believe that you should do this type of stuff is to increase manufacturability of your parts and your designs. So the more practice you get in doing things, the more you know about the terminology and the tools that are used for that fabrication process. So for example, for CNC, when you have experience milling or using a lathe, you know the terminology for all these tools, you know where to get these tools from. And that translates directly into design. So when you have a design with like a really odd feature, like undercut or whatever, you know right away whether there are tools out there in stock that can do this. Because otherwise, you're just kind of blindly saying, I have this feature, I'm going to send it out for a quote. They're going to come back and tell me, this isn't manufacturable, we need to make a custom tool. And you're kind of wasting all that time going back and forth. So if you know about the process, you know exactly what to look for, and then you can tweak your design to fit something that's standard. So like, for example, for myself, I often look at MasterCard, Harvey Tool, conical cutting tools, they do a lot of taper end mills. So whenever I'm designing something, I will always use my knowledge of machining and look to see if there's a standard tool that's out there available. And if there is, then I'll try to fit that into my design, just to minimize any miscommunication I'm going to have with the supplier, and also to make sure that it's manufacturable. So this is just an example of like a really odd part, something that has a pocket and then a cylindrical cutout inside. But hey, there's a tool from Harvey Tool that does this exact thing. So you don't need to have somebody machine this, flip this over, and then machine the surface in a very like strange way. You can just buy a tool and just do this all in 2 operations. So, yeah. Other examples are, this is an injection molding example. So again, if you know a bit about the process, you know how things are made. You know, like if you're looking at this part here, and there's 2 options of making the tool. You know that long, thin tool, so I just described it as hard to machine, right? So you prefer this over this in manufacturing. So you design your part to have tooling like that. Other things, if you learn a bit, like, I mean, with injection molding, it's a bit harder. You can't really like make your own tool and then like do the injection molding. Like that is almost impossible for engineers to do. But you should still strive to learn as much about the process as you can. So again, like minimizing the complexity and trying to keep things as standard as possible. So like having an undercut, if you do it this way, you have to have complex geometry, you have to have like a slider to get that undercut. You can design things differently so that there's a hole here, so that you can actually just have 2 molds coming in. And then looking at things that, this is an example from Proto Labs. You can actually get this physical part and look at it from Proto Labs. So always like trying to learn about the manufacturing process itself can help. Like, so this is just an example of like how the molding process would actually work. There's the A side, there's the B side. There's also this slider here that does this little hole over here. So the more you know about the process, the better you can design to minimize complexity. Another example for sheet metal. So I also have a lot of experience with sheet metal, and the first thing that you're taught is that this aspect ratio you have here is very important. So if you have something that's very narrow, something with very long flanges, it's just not easy to manufacture. Like if you're looking at this picture here, these bends are almost going to hit this tool here, right? So if these are even longer, it's not going to be manufacturable unless people make custom tooling, and that's just going to cost a lot. So again, the more you know, the better. Another benefit, this is like a smaller benefit, but still interesting if you're working in a lot of like industrial or medical device, you need to know a lot about material properties. So there are things like thermal properties, hardness. Hardness is probably the property that you will learn the most from machining. So if any of you have ever tried to machine stainless steel, you will know that stainless steel is hard to machine. And like, if you don't know what you're doing and you're letting your tool rub on the stainless steel work hardens. So in other words, with more strain, it gets harder. So I mean, although this is a small thing, having the hands-on experience teaches you some of these things that you wouldn't have known otherwise. These are probably my 2 favorite slides. So there's a company called Fictive in the US. They're very much like Proto Labs. They do a lot of rapid manufacturing. So this was in their State of Hardware Report 2018. So 29% of manufacturers reported that they often or always receive parts that aren't manufacturable. 66% of developers say they have experience with miscommunication. 74% of manufacturers also report a similar miscommunication. So there's just generally a lot of communication on both sides, from the supplier side, but also from the designer side. And this is my favorite side. So 54% of developers, and I think by developers they mean like designers or engineers. So 54% of us think that we are extremely knowledgeable about the manufacturing process, and 27% of manufacturers agree that we are knowledgeable about the manufacturing process. So like this applies to me too. Like I'm giving this talk and I'm saying that I know a lot about these processes. But really, I mean, like if you ask a supplier, like I make many mistakes as well. I used to work with a machinist, and every day that I worked with him, I learned new things, even though, you know, I machine and I know things all the time. So just knowing more and more of the process can minimize miscommunication and can dial in things faster and quicker and less potential problems with you and your supplier. It also helps with, like Nick and I were talking about this, it also helps with client management, like, and expectations, right? So a lot of clients, even some engineers, like they don't realize that, for example, when you CNC something, you send your part out to them, the people have to program it, right? They have to program how the machine's going to cut everything away. And also they have to then make scrap. They have to make 1 or 2 cuts of your actual part before they can send you a part, right? So basically like the third part that they make is the one that you're actually getting, even though you ordered a quantity of 1. So just knowing that, you can help manage expectations for your clients, but also for yourself as an engineer. This is this is again an example of improving communications with suppliers with sheet metal. So often with sheet metal, you have lots of bends and you have lots of inserts. So these are like hole cutouts for pen nuts, so thread inserts. So if you've never made a box like this before, you can often fall into pitfalls where either these flanges need to be bent in their exact certain order, and I mean your supplier should know, but they might run into issues. So if you already know this and you've designed knowing that okay, these need to be bent in a certain order, then you can communicate that to your supplier and things will be a lot smoother. Also, spacing between inserts, like from a bend point, is very important too because they have to use tooling to put those inserts in. And again, if you haven't done this before, you could design something that's really close to a bend and it wouldn't be able to be manufactured. So this is a case study of a product for a fuel cell application. So this is a gas nozzle for hydrogen vehicles. It's got an infrared receiver on here, and what it does is it plugs into the gas nozzle the gas tank of a car. The tank for hydrogen vehicles has a transmitter that transmits data like pressure, temperature, etc. of the tank to the gas station. So it like knows how fast it can fill, it knows like safety and control. So this is a product for a company that, well, the company makes this part too, but what they wanted to do is they wanted to make a handheld device for people to test the functionality of this. So operators would take that handheld device, go to each kiosk, press a button, test the infrared receivers are working. And so this is a pretty simple part. The only caveat is that it has this like little nub here that's sticking out, and that actually needs to be made into the cylindrical gas nozzle that you saw on the last slide. And it needs to be a pretty tight tolerance fit. So, sorry, can you go back? So, knowing about the machining process, we were able to predict problems and solve them earlier. So, one problem with this is that this is a cylindrical piece. So if you're trying to machine this, there are 2 ways to do it. You machine the top, you machine the bottom, but to do this, you would either have to flip it over for a third operation to machine this cylindrical part, or when you're machining this face, you have to do what's called surfacing. So you have to literally take a tool and you have to just like keep cutting it like this until it's round, which takes a lot of time and it's really expensive. And also, flipping it and doing a separate operation is also time consuming and expensive because you have to make fixtures to dial it in, then you have to like find your zero and everything, and like there are potentials for errors. And because this is a very tight tolerance mating feature, like that could potentially have issues. It might not. Your supplier might be really good and it might be totally fine. But thinking about that process beforehand lets you make decisions to mitigate that error. So what we actually did is we thought about that beforehand, and so when we found suppliers to do the machining, well, we said, well, why don't we just find a 4-axis supplier, like someone who can cut the top and the bottom and then also do that cylindrical feature without having to take the part off or without having to do anything fancy like surfacing. So we actually found a really good supplier that does a lot of 4-axis horizontal milling. So this whole pallet spins. So you have your part on here, and you machine that back base, and then it turns, and then this part can machine that cylindrical feature, like just in one operation. And this actually became cheaper than doing it the other way by taking it off and having another operation. And it's also much more accurate. So knowing some of this beforehand can help you mitigate problems later. Another good reason is if you have knowledge of making things and you also have access to tools. So not everybody has like in-house tools, but if you have access to things like displays, makerspaces, and laser cutters, you can iterate really quickly, and you can also spur innovation. So I'll talk about iterating quickly first. So this is a custom robot for, I'll kind of give like the fullest notes, but it's a custom robot for coring out little bits from tumor biopsies. So each one of these blocks is a little biopsy from a patient who has like terminal cancer, and what they want to do is they want to automate the process where they have like a coring tool, they core out a cylinder and they put it into a tube, and then they go and sequence that bit of tissue. So all of this you see here, this was all made in a day. So knowing how to make things, and if you have tools like a laser cutter or water jet, you can cut all of this out in one day, and then you can iterate super quickly. Which is handy for basically any project that you're working on. Again, other examples of having the in-house tools to be able to iterate. So all of this again was made in one day on a water jet, and like Angela alluded to when she talked about like 2D cutting and laser cutters, you can do a lot with 2D parts. You just need to be clever about it. So this is a Peltier device to heat and cool samples on that robot that you just saw. And again, all of this was just made on a water jet cutter. So it was all 2D parts. Obviously this had to be bent, but really fast iteration on any design that you have. And obviously this gets you only so far. Like if you have plastic parts, like a wearable or something, you might not be able to do this, but just having these tools and knowing how to use them can help you iterate a lot quicker. It's another example of doing something yourself, like with machining. So these are actually 45-degree mirrors. So you can buy acrylic mirrors just from McMaster. So like the top layer is the aluminized reflective surface, and everything else is just acrylic. So again, if you don't have experience machining and you don't have the tools, like you would have to send this out to a CNC shop, and you have to spend 3 days or like even up to a week to get that part back. But if you know how to do some machining, you have the tools, you can take this and you can just create a 45-degree mirror in an hour. So these parts were bought from McMaster. They were water jet cut out to like little pieces. They were put in a device, used the tapered end to just cut over the 45-degree angle. So again, really quick iteration. Some examples of 3D printing. Obviously, you guys will probably know about that. 3D printing enables really fast iteration as well under certain circumstances. So I'll talk a little bit about spurring innovation as well. Quite similar to what Angela was talking about in her talk for like emotional safety and feeling that you can make mistakes. If you have the tools and you know how to make things, you can also come up with some really neat ideas. If there's no pressure of cost and no pressure of time, you just have tools available, you can do crazy things and you can solve problems or come up with new ideas really quickly. So this is an example of a vacuum forming machine that we made in-house. So when people were taking tumor biopsies from patients, what happens is you take this giant needle, you core out some tissue from, like, say, your liver, and you have to freeze that into a tray really quickly. And doctors were having a lot of problems with what's called ischemic time, which is time in which your tissue is outside in the air and your DNA and RNA is degrading. So there actually wasn't a budget for this, there wasn't a project for this, but because we had the tools available, we thought, why don't we just try something? So we ended up experimenting with different tray geometries. So we ended up making our own trays for the tissue to be frozen. And we did this, again, with the water jet. We just like cut 2D parts, built our own vacuum former. And we actually used our knowledge of 3D printing and our knowledge of material properties for ABS. And we 3D printed molds for the vacuum forming. And that's what you see here. So, trying crazy things like this, if you didn't have the tools and you don't have experience doing this kind of stuff, it would be very difficult or just wouldn't happen at all. Just an example of doing urethane casting, 3D printed parts, which is kind of like my pet project right now. There's been some people like trying to do this, but so for an engineering design company or even like industrial design, you guys work with a lot of like looks like prototypes, right? And often like you design something, you 3D print it using SLA, or you'll make something and get some material then cast it. What we're always trying to do is we're always trying to push the boundaries for like doing things faster and more efficiently. So one way of doing this is to 3D print molds for your casting, so that instead of having to get a company to machine something and then do a silicon mold and then pour the urethane casting in, we're looking at ways of 3D printing like elastomer molds and then pouring the urethane right into it to cast the product. It's basically skipping a step. Anyways, again, something that like, you know, you can try crazy things and they may or may not work, but like you can do it. So.
Did it work?
In progress. Yeah, so there are people who have done this. Like this is an example from a company called Javelin Tech, which is like a Canadian 3D printing distributor. And like this works. Like this is a 3D printed mold. This is a soft durometer urethane. So like they just pour this in and this will just pop out. So some people have done this before, but there's just not a lot of like research being done on it. Similarly to like the last slide for vacuum forming or 3D printed molds, like there's not a lot of literature out there showing that this can be done, but like if you have the tools and you know a little bit about the process, you can try it. So yeah, like, people are starting to do this. So.
There's still some surface finishing you have to do after.
Yeah, I mean, yes, like so typically people will machine the master and then they polish it and everything and then make the silicone, right? So yeah, like if you're doing it this way, you're basically skipping that step and you're 3D printing your master. So obviously when you 3D print your master, you're gonna be limited in terms of surface finish, right? So yes, like there's some stuff that you still might need to do, but the goal is to kind of just like 3D print something and then boom, like just pour urethane into it and then just have your part. But yeah, it's a work in progress. So I think this is the last kind of point about why it's important to get some hands-on experience. But basically to qualify suppliers more easily. Machining videos are awesome, so I had to put some GIFs here. But the more you know about the process, the better you can go to a shop. Like say here, if you don't live in Hong Kong, you don't live in China, and you want to vet, or even if you do and you want to vet a supplier, the more you know about these machines and how they work, the better you can walk into a shop and you can just say, okay, you guys have good machines, like you guys look like you know what you're doing. Otherwise, you just kind of look and you're like, cool, a robot, it's cutting stuff. Like, that's great, like that's what I need. But yeah, so in general, more axes means more complexity and which requires better programmers. So that's always a good thing to know. And like I was just saying, machines and tools are a pretty fair indication of shop quality and the shop's investment into building tools. So yeah, I wouldn't describe this thing. No, it's not. Okay, fine. So this is a lathe, what's called live tooling, and so you can do milling while turning. This is a 5-axis milling machine, and then this is a horizontal 4-axis that I was talking about earlier. So yeah, knowing this stuff is important. The last bit is just a bit of like electrical stuff. So most of the stuff I've been talking about is mechanical. It's also really important to learn how to do things like surface mount soldering. So Angela touched on this in her talk that like, we always design with contingency so that we can potentially fix something if we have to. And learning how to do this is really important because sometimes your PCB may have issues. Like if you're just doing a short run, sometimes they may have issues. You can actually rework it and get it to a satisfactory standard. You know, if you're just making 5 and you only need to like rewire one thing, like if you don't know how to surface mount solder, you basically have to re-roll your whole board, you have to get everything assembled and do it all over again. But if you have this experience, like it's just so much faster to just do things on the fly. example of like hand solder devices. Like we don't recommend doing this, but it's just like an example of like what you can do. So all of this is hand solder. So yeah, key takeaways: get your hands dirty. It's really fun to make things, and it's like really fulfilling as an engineer or designer to do that, but also it'll make you much more proficient. So okay, well, what if you can't afford all these like fancy tools, blah blah blah? Again, there are places like this, maker spaces, where you have laser cutters, you have a drill press, you may have like lathes or mills. Take advantage of that. Go into those places and start using the equipment. 3D printers, obviously, sheet metal bending tools. There are also other ways if you as a company want to start investing in this stuff. You can buy used equipment. There are a lot of really cheap laser cutters or like little mills and CNCs that you can buy. You will still learn a ton from them. If you love laser cutter, starts at $5,000. Take night classes on machining. There are places that you can do that, like HPU probably has something like that. So, yeah. This is just an example of like what you can do with 2D fabrication. Just like that. Yeah, soldering stuff. So there are what's called IPC standards for soldering and rework. There's a really great document online just on the IPC website that you can read, and you can like learn how all the professionals do rework and soldering. So that's a great way to learn how to do surface mount soldering. Also, as Angela talked about, watch a lot of videos on YouTube. I watch machining videos all the time on YouTube. So it's like a really great resource. What's that? Yeah. Useful resources. So these links have a lot of like design tips for DFM or prototyping that I didn't really talk about. Again, because they all exist already. But Proto Labs, Dragon Innovation, Fictive, they have a ton of really useful information. So if you as a designer want to like learn some more things about the manufacturing process and how to design for manufacturing, like check those links out. The IPC standards, as I mentioned, for learning how to do surface mount soldering and rework. Proto Labs has like a neat little online coding system, so it'll basically tell you whether your part can be manufactured or not, like automatically. But the only thing is like take that with a grain of salt, because Proto Labs has very tight constraints. So sometimes they'll tell you things that they can manufacture, but doesn't necessarily mean it can't be made elsewhere. And there's just an example of injection molding parts and design guides that Proto Labs gives you. So it's always useful to like get a bunch of these to learn about injection molding. And then my favorite book, the Machinery's Handbook, it's basically like the Bible for learning how to do machining and stuff. Yeah, I think that was it. So yeah, that's a question.